positive definite matrices. The definition is this. A real symmetric matrix is positive definite if its eigenvalues are all positive. A real symmetric matrix. So if it is not real or if it is not symmetric, by our definition, the one I stated here, it cannot be positive definite. Now that particular part of the definition, some people don't like it. So there may be some people who might say that the matrices don't have to be symmetric to be positive definite, or they need to have is a property that all the eigenvalues are positive. And there are good theoretical reasons for it. And there was a mathematics paper that I saw while doing some research on it that actually argued for that. But I think the general definition is for real symmetric matrices, and that's what we will stick to. So real symmetric matrix is positive definite if its eigenvalues are all positive, real, square, and symmetric. The same definition in mathematical lingo. For all eigenvalues, they have to be positive, strictly greater than 0. If some of them are actually 0, then we call such matrices positive semi-definite. So remember, if an eigenvalue is 0, that means the matrix itself is not invertible, it's singular. So if it is positive semi-definite with an eigenvalue equal to 0, then A is a singular matrix. So some people do define negative definite and negative semi-definite, but those things are not that common. So let me tell you a bunch of tests for positive definiteness, and there are also properties of positive definite matrices. So the first thing is actually from the definition, are the eigenvalues all positive? Are the pivots all positive? Then the matrix is positive definite. This comes from the Sylvester's law of inertia. And the third one is an interesting one. For any vector not equal to 0, can you show that x transpose AX is greater than 0? And we will see what that means. So I'm not saying try this vector or that vector, but try a general vector and mathematically prove that this product, this triple product, is greater than 0, meaning it's like a full square or something, and then you know that A is a positive definite. Now another test is that if all leading sub-determinants, so I haven't defined what leading sub-determinants are, but if those guys are positive, then the matrix is positive definite. So let me define what leading sub-determinants are. If I have a big matrix, square matrix, real matrix, I look at the determinant of the smallest one starting from the top left. That would be just the first element. If that is positive, that sub-determinant is positive, and I would take the second one, that is from second row and second column. So that little square matrix, 2 by 2 square matrix, also should have a positive determinant, and I'll keep going. And the kth one will have k rows and k columns, and that is the kth sub-determinant, and the nth sub-determinant will be the whole determinant. So every one of them will have to be positive for the matrix to be positive definite. So that's another test. So that is the kth sub-determinant that I've highlighted there. Kth sub-matrix out of which the kth sub-determinant will come. Another one, a matrix B is positive definite if it can be written as B is equal to A transpose A for some invertible A. So let's use these tests and apply the tests in certain cases. Suppose I give you a matrix and tell you that it is positive definite. Is it inverse positive definite? So you don't have to actually compute the inverse, which is a horrible problem by itself, and then compute the eigenvalues. That will be another horrible problem, and then see if they are positive, and that would be brute force way of doing it. But you can apply test 1, which says that A has all the eigenvalues greater than 0. A inverse will have eigenvalues equal to 1 over lambda. The eigenvalues of an inverse are the reciprocals of the eigenvalues of the original matrix. So if the eigenvalues of A are positive, then the reciprocals are also positive. So A inverse is positive definite. If A and B are positive definite, how about A plus B? But you can apply the third test, which is X transpose X, sandwiching the matrix, and just expand it out. You know that this is positive because A is given to be positive definite, and this also is positive. So the sum is positive. So A plus B indeed is positive definite. The next one, if you have any matrix, not a square matrix, any matrix, but full column rank though, the gram matrix A transpose A, is it positive definite? So you can use the third test, transpose AX, and I realized that this guy here, the product of transposes, is actually transpose of a product in the reverse order. And now look at this, is AX transpose and AX. That is just the norm of AX square, and that has to be greater than 0 as long as X is not 0. So A transpose A is positive definite unless AX equal to 0, which means either X equal to 0. It cannot be that AX equal to 0 without X being equal to 0, because we said that it is A is a full column rank. That means A transpose A, which is an n by n matrix, is a full rank matrix. Its rank n is the same as the rank of A. So you cannot have null space. That means you cannot have non-zero X giving you a 0, and that's why the gram matrix is positive definite. Now there is another one which is interesting. A is given to be positive definite. Let's take some matrix M which is invertible, so square and invertible, and take M inverse AM. Is this positive definite? Let's verify that. Let's call this matrix B, and then A becomes MB M inverse. We know that AS is equal to lambda S, and where I see A, I just put the expression I have for A, and I get that. Now I know that M is invertible, so I can take M to the other side with inverse, and then I get B M inverse times S is equal to lambda times M inverse S. So if I just read it properly, I see this vector here, M inverse times S, which is just a vector, and M inverse times S over there, which is the same vector. So B times some vector is lambda times the same vector, which means lambda is an eigenvalue, and that vector M inverse S is the eigenvector. If A is positive definite, then this guy, which we call B, has the same eigenvalues. So since eigenvalues are the same, if A is positive definite, all the eigenvalues are positive, so all the eigenvalues of B are positive too, and B is positive definite. So same eigenvalues. That is interesting. But the eigenvectors are not the same. Eigenvectors are different. So if A is positive definite, so is M inverse A M. Later today, we will call A and B equal to this guy. We will call them similar matrices. Now let's take a look at something called quadratic forms. All these topics that I'm telling you today, the actual computer science application of those things may be dubious. They may not be there. But I'm telling you these things because I'm hoping that some of you later in life might use some of these concepts and apply and find some nice application in computer science. So if I don't tell you these things, there is little chance that these things might occur to you because you haven't been exposed to them. But since now that you have some exposure to these concepts, maybe when you're dealing with some data science problems or some algorithm, you might think that, hey, this looks similar to what our prof told us a long time ago, and maybe I can try that, and maybe you look it up and try it and maybe come up with something that is brand new, may be valuable, and that might expand the horizon of our knowledge, really. So that is my hope. So even though some of these things are more conceptual and theoretical, don't discount them thinking that they are useless. Alright, let's take a real symmetric matrix. So AB and BC. So it is symmetric because B here, and they are all real numbers. And conditions for positive definite. This sub-determinant has to be positive and the whole determinant has to be positive. So A has to be greater than 0 and determinant of A has to be greater than 0. And the determinant of A is AC minus B square. Now let's look at X transpose AX with some general X vector, which is X1 and X2. And if I do the expansion, what will I get? A is equal to A, B, B, C. I'm taking X, X1, X2, X transpose AX. Write it out more explicitly. X1, X2 is a row, A, B, B, C matrix, and X1 and X2 as a column. If I do the multiplication here, I multiply out what I will get. A multiplying X1 there and X1 here. So I will get A X1 square plus I'll get C X2 squares, and in between you will get X1, X2, the cross term, with B and B again in two different ways. Now, if you look at the expansion that I've written here, that is a pure quadratic. That's what they mean by a pure quadratic. It's a polynomial in which each variable x1 and x2 will always appear in order 2. So there is no bx1 term or bx2 term. There's only bx1, x2. It is a quadratic in x1 and x2, or x2 by itself or x1 by itself. No constant terms. Now, suppose I take an example. A and B I give numbers, but for C, I keep it as a C. Then I ask you the question, what's the determinant of this matrix? 2, 6, 6C. That turns out to be 2C minus 6 times 6, 36. And I want that guy to be positive for the matrix to be positive definite. So C has to be greater than 18. If it is greater than 18, then 2 times something greater than 18 minus 36 will be positive. So if I take 20, so what I have here, 20, and if I do the multiplication just like I did here, ax1 square, so 2x1 square, 2b x1 x2, so 12 x1 x2, and 20 x2 square. So that's what I will get. And if I want to prove that this is positive, what I will do is to try to write this as sum of squares. So if if I do that, I can pull out 2 and then see that it's x1 plus 3x2 square. So that will have 6x, x1, x2 times 2. So that is, I get 12, I get this guy, I get this guy. And the last one is 9x2 square times 2, that is 18. But I need 2 more, so I add 2 more there. But you can see that it's got 2 terms, and each one of the 2 terms will have to be positive because you see only squares there. It doesn't matter what the value of x1 and x2 are, this will be always positive. Any non-zero value of x1 and x2 will give you positive numbers here. That is how you would prove that for a general x1 and x2 or general vector x transpose Ax is positive, and so A is a positive definite matrix. Now, one more thing I want to highlight about this. Suppose I want to do a Gaussian elimination on this matrix here. You would multiply the first row by 3, subtract it from the second row. So this will become 0. And the second one, multiply this by 3, so 18, 20 minus 18, I'll get 2 there. So I'll have pivots 2 and 2. And the multiplier that I used is 3. And if I look at the completion of square, I see 2's here and the 3 there. So completing the squares to prove that it is positive definite is actually has row reduction in it. So you can retrieve the pivots and multipliers from the square that you're writing down, which is interesting. All these things are interconnected in the world of linear algebra. Nothing stands on its own. Quadratic forms. It's a deep field. It's a portal to a deep field. Each one of the topics that we did today is actually a portal to a deep field. Complex matrices, of course. Markov matrices, that is a starting point of Markov chains, hidden Markov models, mathematical modeling, and positive definiteness, and this one also.